In this video, we're going to introduce the concept of the mole. We're introducing this concept in the context of stoichiometry, which is the field of chemistry that tells us how the transformations from reagents to products in chemical reactions are from a quantitative level. Right? So again, the overall goal of this section is going to be to predict with quantitatively, okay, how many grams of A are we going to have to mix with how many grams of B to generate a target amount of product AB. Now we know that these transformations take place at the atomic level. Okay, so this reaction renders this means that one atom of A is going to combine with one atom of B to generate one molecule of AB. The problem is that while that is true, we don't work at the atomic level. Generally, when we go to the laboratory, we actually work with microscopic samples that contain not one atom, but very many millions of atoms. Right? So the question is, how do we scale a concept that is atomic in nature to something that we can use that contains many millions of atoms? Right? So that is actually the concept of the mole. The mole is going to be the bridge that allows you to connect the atomic world, okay, the world of chemistry, of chemical reactions, to the macroscopic world, which is where we operate. Okay, so then let's try to define what a mole is and see what the significance of that concept turns out to be. All right, so one mole is trivially defined as the following. One mole of anything, one mole of an atom, one mole of molecules of anything is equal to 6.022 10 to the 23 entities. Right, so one mole of A will be of atom A will be 6.022 10 to the 23 atoms of A. Right, now this number looks a little exotic, but it actually is very well justified, as you're going to see in the next calculation that we're going to do. Okay, the calculation is going to be trying to figure out what is the mass, the weight, of one mole of the carbon-12 isotope. Okay, so let's start with that. And the question would be, please calculate in grams, okay, which is something that we can go to a scale and measure how many grams are there in one mole of pure carbon-12 atoms. Right, we know that from the atomic mass discussion that we just had in the prior video, the mass of the carbon-12 isotope is exactly 12 atomic units. Okay, so one carbon atom has a mass of 12 AMUs exactly. Right? That is the mass of one atom of carbon. Okay, 12 AU per atom. And again, the question is, well, if we take now one mole, these many atoms of that particular carbon-12, how much would that be? How would be the mass of that in weight? Okay, in grams. All right, so here we go. The first thing we're actually going to do is to transform the mass of this isotope into kilograms. Okay, and we know that the conversion between AMUs and kilograms is equal to 1.66 10 to the minus 27 kilograms. And that is per AMU. Okay, so up to this point, notice that this AMU unit cancels with that AMU unit, and here we will have the kilograms that we have per atom of carbon-12. Of course, that will be a very small number because an atom is a very small piece of matter. Okay. Now, we're actually not taking one atom, we're taking 1 mole of atoms, right? So we're taking 6.022 10 to the 23. We have atoms per mole. Okay? All right, so then what we actually have is that this atom will cancel out with atom, and then what we have is that the mass of 1 mole of carbon-12 will be exactly, you take that to your calculator, and that number happens to be 0.012 kilograms per mole. Okay, but because we have 1 mole, this is simply 0.012 kilograms. The same thing is to say that we're actually going to have 12 grams of carbon in 1 mole. Okay, 12 grams of carbon per mole. Okay, so this is very interesting. Notice that here, you actually have that is the mass of 1 atom of C12 only. Okay, 12 atomic mass units. But if you take a mole of that C12, a huge amount of that C12, these many atoms of C12, that actually happens to be exactly the same number, but now we actually have it in grams. So this really reflects very nicely the usefulness of a mole. right? You're able to scale atoms to the gram scale. That is what the mole allows you to do. Okay, so again, if you know that if you now take a sample of C12 that weighs exactly 12 grams, then you will have exactly an Avogadro number of atoms in that sample, where this is what we call Avogadro's number. Okay, and today that is Avogadro's number. That is the number of entities that you have in a mole. Right, to further reflect on the usefulness of the mole, we're actually going to do one more calculation that is again going to show how we can connect the macroscopic world, the world that we operate, to the atomic level, okay, which is where chemical reactions really take place. Right, so the example that we're going to be working with is going to be to predict the number of atoms that we have in a given mass of carbon. Now, this is not going to be carbon-12. It's actually going to be naturally occurring carbon, which, as we know, contains mostly carbon-12, but a little bit of carbon-13 as well. Okay, so we're going to go to nature, get pure carbon, weigh that carbon, and then predict how many atoms we have in that particular mass of naturally occurring carbon. All right, so the amount that we're actually going to take is going to be 1 nanogram of naturally occurring carbon. 1 nanogram is equal to, with two significant figures, 1.0, 10 to the minus 9 grams. Okay, that is going to be our sample size. And again, the goal is to calculate how many atoms we have in exactly that mass. 1 nanogram, as you can imagine, is something that is very, very, very small. Okay? Now, the way that we're going to do this is as follows. We know that if we go to the periodic table, the mass that we have right there, that 12.01 for carbon, is going to be the mass of 1 mole in grams. Okay, so the goal is going to be to then, from that mass in grams for a mole, we're going to try to figure out how many moles we have in this tiny little mass. And then, because we know that 1 mole contains an Avogadro number of atoms, then we'll be able to calculate how many atoms are in that particular mass. Okay, so again, first we take this mass, convert to moles, and then from moles you will convert to atoms. Okay, so you can see how the moles act as the bridge between our balance, right, our laboratory, and where the chemical transformations take place, which is at the atomic level. All right, so let's actually do that calculation then. We have 1.0 10 to the minus 9 grams of carbon. Okay. And we know that we want to calculate the number of moles. We know that in every mole of naturally occurring carbon, we actually have 12.0 grams of 0.01 grams of carbon. Okay, that is the mass provided by the periodic table. And again, that corresponds to the mass of exactly 1 mole. Okay, so up to this point, we will actually have that the grams cancel. We'll have the number of moles present in that particular amount, in that nanogram of carbon. But we actually also know, so we actually have crossed with this conversion, we have crossed this from mass to moles. That is provided by the mass given in the periodic table, again taken in grams per mole. Now, the second transformation would be to actually then convert moles to atoms, and here we can use Avogadro's number. Right? We know that there's 6.022 10 to the 23 atoms per mole. Okay, so the mole will cancel with mole, and then we will have how many atoms you have in that particular amount of carbon-12. Okay? It's not carbon-12, but naturally occurring carbon. When you actually do this calculation, this happens to be 5.0 10 to the 13 atoms, which is the same thing as 50 trillion atoms present in a tiny little amount of carbon, which is in this case 1 nanogram. Of course, we could have taken a different amount. For example, instead of a nanogram 10 to the minus 9, we could have taken a gram, which is something that is much easier to weigh than a nanogram, and of course, these would have changed by 9 orders of magnitude, right? So the answer would have been 5.0 10 to the 22 atoms in that particular sample. Again, this problem is just put here to illustrate how useful is the concept of the mole, right? How it allows us to go from the atomic level to the macroscopic level, back and forth, and this is going to be extremely important going forward.